Hello and welcome to our next lecture in inferential statistics. Today we're going to be talking about confidence intervals. So statistical inference, even in terms of classification, mainly is discussed in terms of hypothesis testing and estimation. So these are the two broad categories in statistical inference. And hypothesis testing is something that we've discussed in good detail in this class. We've talked about single and two sample tests, various tests. Today we're going to be primarily talking about estimation. And you might notice that almost any text that talks about statistical inference talks about these two topics, and some of them might be introducing estimation or confidence intervals before hypothesis testing. But that doesn't really matter. Essentially, these are two sides of the same coin, if you may. And so today we're going to be talking about estimation. Now, the idea behind estimation is that estimation can be in terms of point or interval. What we mean by that is it's the same core concept as what we introduced with inferential statistics during hypothesis testing, which is that we are interested in some population parameter. Okay, what we mean by that is that there is this concept. So the examples that we've used in this class are things like amount of phosphate in our blood, the height of 10 standard students in public schools in India. In all these cases, you define some population and you're interested in some parameter. More often than not, we've discussed the parameter being the mean. Right, so what is the average amount of phosphate in blood? What is the average height? But it does not. That's just one of the parameters. That's the most common one. But it can be other parameters. So stepping back, we're interested in some population parameter. But you don't know this parameter. It's like it's some truth that you don't already know. If you did know that, there would be no need for any of this or any of the statistics. But what you do have is a sample. So you have 5 data points, 10 data points, 20 data points, 30 data points, some sample from this population. And what you're most interested about this population parameter. So in hypothesis testing, you would hypothesize that this population parameter is equal to 4.8 or 2.3, or it's less than 4.2. And then you would go about and look at this sample and see if that's true or not. With estimation, you're not having any hypothesis. You're not having any hypotheses in mind in that sense. What you're trying to do is you're trying to take the sample, and with point estimation, you're trying to come up with a single point estimate of the population parameter. And that might seem fairly straightforward, right? So for instance, let's say you were interested in the population parameter, which is the average amount of phosphate in blood, and you took some sample, and that sample was about 20 data points. A simple point estimate of the population mean could be the sample mean. So you take the sample of 20 data points, take their average, and that's your best. That could be one of your best point estimates of the population mean. So point estimate just means you're making as good a guess on the population parameter based on the data that you have. But today we're going to be talking, and more interestingly, this is what gets this is what people are more interested in, which is interval estimation in the form of an interval. So this goes back to again the core concept with hypothesis testing, which is fine, you don't know the population mean, you have a sample mean, and you acknowledge that if you go take another sample of another 20 points, you might not get the exact same value. And both these values, the first time around and the second time around, might not be exactly equal to the population mean. Okay, if it's not exactly equal to the population mean, then can I come up with some range around my point estimate? Right, so I have a point estimate which is actually my sample mean. My sample mean is my best bet, let's say, at my population mean. But I acknowledge that I might not have exactly hit target. Right? The population mean might be a little higher or a little lower than my sample mean. In which case I ask the question, can I come up with a range around this sample mean, by which means it's essentially like I'm giving myself a margin of error by which I'm fairly certain that I've covered the population mean. So that's the goal that we're going to embark upon. And in many ways, it's the same math. Because we've introduced hypothesis testing, it becomes a little easier so that we can reason by the same logic and math that we've already discussed. So let's do that. So the core idea is that let's take an example that we've looked at many times, which is that we might be hypothesizing that the amount of phosphate in blood is equal to exactly 4.8. Now we discussed that in confidence intervals, you don't have this number. You don't come up with a hypothesis. You're only interested in coming up with some bounds around your point estimate. So what you essentially do, one way of thinking about confidence intervals, given that we have already introduced hypothesis tests, is, well, for different values of mu naught. So let's say you have some data set and you calculate some x bar, right? Essentially 4.8 gets plugged in out here to calculate your z statistic. If you're doing a z test, you're given a sigma. If you're doing a t test, you take an s, but in either case that gets plugged in. N is again the number of data points, so you get some z value, some z value that's out here, and based off of that z value you calculate some probability. You calculate a p-value. Now the core idea with hypothesis tests was that if this p-value is really small, right, you reject the null hypothesis. Okay, so the question with confidence intervals, one way of thinking about it is, given that I don't have some hypothesis, I ask myself the question, within what range can my mu's be such that I will calculate a z such that I will get a p-value which I will not reject. Okay, I'm just going to repeat that. Given that you don't have a mu naught, you can think of a confidence interval as what is the range of values that mu could potentially be such that, given that for a given data set you get some x bar, some sigma, some root n, such that you will calculate a value z, such that you will get a p-value which you will not reject. So if you won't reject that, that means you need to have some bounds, right? Suppose you start off by saying, well, I'm going to reject any p-value less than 0.05. So that's something you started off with. Now, given that you started off with that, then is there some range for a given data set? Is there some range of mu's, okay, such that you would not be rejecting this hypothesis test? And essentially, to compute that, all you do is just rearrange the terms out here. So you keep the mu naught on the mu or the mu naught. I'm using those two terms here interchangeably. But you keep that on one side and you essentially move the terms to the other side to get this formula for confidence interval. So typically, if you know the formula for the hypothesis test or the test statistic, you can just essentially rearrange it. But the core idea is that this is your point estimate, which is your x bar. So for your best estimate of mu is your x bar. But you create a margin of error, or you create a range around it as plus or minus the z associated with this alpha, and alpha here is that 0.05 that you said. Essentially you said within a certain range, right? So within that range, and sigma and square root of n are the same. Okay. Another way, a more formal definition associated with confidence intervals is that if we were to repeatedly take identical samples of the same size and build similar confidence interval bounds for each sample, then you're building a bound such that 95% of such confidence interval bounds will cover the true mean. Or in other words, we are 95% confident / certain that the true mean mu is within our confidence interval. So for single sample tests, the process of creating confidence interval is fairly straightforward. I explained to you how in the z test, it essentially just becomes a rearrangement of terms, and this sigma by this concept of sigma by square root of n essentially goes towards the z, and then the x bar goes here such that it's a plus or minus, and that's how you get the formula for that interval. Okay, the same core idea for the t-distribution. The formula is no different, except that the t-distribution gets also defined by the number of degrees of freedom. So not just the alpha, but the number of degrees of freedom. And in all these cases, mind you, because I'm putting a plus or minus, this is the equivalent of the two-tailed z-test or the two-tailed t-test. You could also create a one-sided bound if you were interested, and that would be, again, the formulaic equivalent of having a one-sample test. Again, it'd be the same sigma divided by square root of n. The formula itself won't be different, but the way this alpha gets used up will be different. Okay, again, it goes back to the core concept of how you would shade that region under the probability distribution. Okay, with the chi-square distribution, that rearrangement is not obvious. To some extent it is, but the plus or minus is not, because you don't have a plus or minus term. It's essentially like this sigma naught goes out here, the chi-square distribution comes down here, but the way we differentiate between the lower bound and the upper bound is by changing the alpha in the bottom of the chi-square distribution. So it's the same rearrangement. It's the same core concept of taking the hypothesis test and rearranging. That is, in this case, it would be to put the sigma naught out here and bring the chi-square down here, and you would have the same formula that you see here, but you get an upper bound and a lower bound by looking at the 1 minus alpha by 2 and alpha by 2. And by the way, this notion of alpha by 2 depends on how you define it. Now, if you say I want a 95% confidence bound, that means you're left with 5%. And if it's a two-tail test, that 5% gets divided into 2.5% times 2. That's how you get the alpha by 2. So it really depends. If someone starts by stating alpha, and you know it's a two-tailed test, then technically the correct way to do this would not be to just have an alpha out here, but it would be to have an alpha by 2, so that you're being technically correct. And the same thing goes for here as well. You'll have an alpha by 2. Okay. Again, the same core idea with respect to the z-test. If this alpha is more a generic term that I've used out here, so if somebody comes and says I need a two-tailed test, so there is a plus or minus and the alpha gets divided by 2, but if it's a one-sided test, that alpha can stay as alpha. So it depends on how it gets formally defined. Typically, if it's a two-tailed test, you'll represent it as alpha by 2. But it's, again, if you look at it, it's the same rearrangement from your test statistic to create the confidence interval. So the same idea goes towards two-tailed tests. Just to give you an idea of how it works for a two-tailed test, I've given a single sample for the z-test. For the t-tests and the proportion z-test, we've consciously left it out. That might be a part of your assignments that you could work on. But the idea is the same. We are interested in this term. We're interested in the term x1 bar minus x2 bar. Okay? And so we want to create a confidence bound around x1 bar minus x2 bar. If you remember, the simple way of thinking about x1 bar minus x2 bar was to say, to test the null hypothesis that x1 bar is equal to x2 bar, but that's logically the same as asking the question, what is the confidence bounds around x1 bar minus x2 bar, and seeing if that essentially covers 0 or not. Of course, this d naught is an extra term. Suppose you were interested in a hypothesis that looked more like this. If this was your null hypothesis, then you would have this d naught being something non-zero. Otherwise, d naught is just equal to 0. Okay, but this is the idea, right? So you are interested in some bounds around the term x1 bar minus x2 bar. And again, you would do the same logical rearrangement. This goes here, and the bounds go around x1 bar minus x2 bar, and you're essentially creating bounds around this value. Okay, so there's x1 bar minus x2 bar, and what is your range around that? Okay, great. Again, similar to the chi-square test, the F test is not so straightforward. So I'm including the formula associated with that out here. You do the same thing that you did with the chi-square test, which is you have the same s1 squared by s2 squared. That's your core upper bound and lower bound, but you divide by this f kind of comes down and you divide by that, but the lower bound is 1 minus alpha by 2 and the upper bound is alpha by 2. Of course, also remember that when this is a two-tailed test, the alpha that you see here becomes alpha divided by 2. If it's a one-tailed test, meaning you just had a plus or a minus, you can keep that as alpha. Okay, I hope that clarified this concept of confidence intervals. Thank you.